So we're live. We're going to do some trigonometry review. For those of you who are on live stream, you can type in any questions you have regarding the exam, whether it be questions from the review sheet, from the homework, or whatever you may have. So any questions, please feel free right now to ask them. So why don't we look at how to prove trig identities first. So in your review sheet, it's section number 6. So we're going to proving trig identities. And there's many to choose from here. So let's look at number 2. So number 2 says 1 over 1 minus sine squared x equals 1 plus tangent squared x. So this is something that I want to show that's true. I know it's true. The assumption is that it is true. So I want to show that it indeed is. And how do we go about doing that? Well, we want to show that the left-hand side of the equation is equivalent or the same as the right-hand side. And usually the approach is that we start with the left-hand side or we start with the right-hand side, either way. But the idea is that we apply certain trigonometric substitutions, and we have to apply some algebraic procedures and steps so that we can go from the left-hand side to the right-hand side. So we need to have a couple of trig identities and formulas already stored in our heads. So let's start with the left-hand side. The left-hand side says that it's 1 over 1 minus sine squared x. Now, this should raise an alarm, and we should be able to realize that 1 minus sine squared x is an equivalent expression for cosine squared. So I can write this as just simply cosine squared x. You see? So I replaced the denominator with its equivalent expression. So it's cosine squared x. Now, 1 over cosine squared x, this is a reciprocal of cosine. And the reciprocal of cosine is secant squared x. Right? This goes from here to here. This is also, so every step I'm taking is a good step. It's a step where I'm just replacing with something that's equivalent. So 1 minus sine squared x is cosine squared x. 1 over cosine squared x is secant squared x. And then finally, I see that, wait a minute, there's a connection between secant squared x and the right-hand side, which is 1 plus tangent squared x. And the relationship is that they're exactly the same thing. They're equivalent. Secant squared x is the same as saying 1 plus tangent squared x. So I just showed that the left-hand side of my equation with some substitutions and pretty much it. Substitutions, I show that the right-hand side is indeed the same thing as the left-hand side. And with this, I am done. I have proven or shown to you that this is indeed a true equation. Okay? So that's number 2. All right. So we can do one more of these. Let's look at number 3. And all of these pretty much go about the same way. So number 3, we have 1 minus cosine squared x, parentheses, 1 plus cotangent squared x, this equals 1. So I want to show that 1 minus cosine squared x times 1 plus cotangent squared x is the same thing as or equals 1. So again, left-hand side. I want to go from my left-hand side of the equation, which happens to be 1 minus cosine squared x multiplied by 1 plus cotangent squared x. And then I ask myself, have I seen these expressions before? And you should be able to answer and say yes. I've seen that 1 minus cosine squared x can be rewritten as sine squared x. And I've seen that 1 plus cotangent squared x is also cosecant squared x, right? So this expression here becomes this, sine squared x, and this expression here becomes cosine squared x. Now, cosine squared x and sine squared x, how are they related? Well, the nice thing is that cosine squared, not sine squared, and cosecant squared x, I can rewrite this as 1 over sine squared x times sine squared x. Cosecant squared is the reciprocal of sine squared. And when you multiply anything by its reciprocal, right, you see these expressions here, quote unquote, cancel, and we are left with 1. And the 1 is exactly the right-hand side. So again, I have completed the proof here because I've shown through some substitutions and a little bit of algebra that the left-hand side equals the right-hand side. So to really do well with the trig identities, proving them, you need to know that sine squared x plus cosine squared x equals 1. So these are formulas or identities that you must know. That you must know. So this is one of them. From here, I'm going to call it little a. I can write that sine squared x is equivalent to 1 minus cosine squared x. And this here was known as the Pythagorean identity. Part B, I know that cosine squared x equals 1 minus sine squared x from the same identity. The second thing I should know, and from the same identity, I can divide everything by cosine squared x, and I'm left with 1 plus tangent squared x equals secant squared x. And similarly, 1 plus cotangent squared x equals cosecant squared x. So these are the identities that I must know and be able to recognize just by glancing them. So in a way, I want to commit them to memory, but in reality, all you really need to know as a basis, as a foundation of this, is sine squared x plus cosine squared x equals 1. So proving identities. All right. Let's see what else we got. Now let's look at simplifying trig identities. So simplifying them. So simplifying trig identities is related to proving trig identities. So this simplifying things is just really applying algebraic and substitution steps to the expression that we have, so that we can get them at its simplest form. We want so we're going to get, for example, let's look at an example. Number 3, sine squared x times cosine x. And so this is an expression here, and a trigonometric expression, because I have trig in this expression. And I want to see, can I simplify it? So normally in algebra, we always want to simplify expressions. And one of those ways to simplify, one of those methods or procedures to simplify any expression algebraically is by factoring. So we notice I have a cosine cubed over here on this term, and I have a cosine on this term, and they're separated by an addition symbol. So I can say, hey, I have a common factor among these two terms. So I can factor it out, factor cosine x. So when I factor it, I get cosine x. And if I factor a cosine x from cosine cubed, I'm left with a cosine squared. And if I factor a cosine x from this term, I'm left with a sine squared. Now, the nice thing about this is that cosine squared plus sine squared is the Pythagorean identity. So I can say, so just make sure you see that I'm taking this expression and writing it in an equivalent form by factoring. And then I realize, hey, this guy right here, this equals 1 because of the Pythagorean identity, which I should know. So this whole thing results into 1, and cosine of x times 1 is simply cosine of x. So what does this expression simplify to? It simplifies to the simple and singly expression for cosine. So cosine cubed plus sine squared x times cosine of x simplifies to cosine of x. And this is the same idea that we apply to proving trig identities. So when we prove trig identities, we already know what we're trying to get into, right? We already know what the expression it should look like, left-hand side with the right-hand side. When we simplify trig identities, we're simply trying to see, hey, is there a way that we can simplify it? What can we do to simplify it? That's number 3. Let's look at number 5. So we have 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. So alpha is just another Greek variable. It's a variable. We could use theta or x or y or z or any other variable, but here we have alpha. Now the question becomes, how do we simplify this? So maybe you're like, I don't know. Looks kind of complicated. Whenever we have something that's complicated, we always want to see, can we solve a simpler problem? Can we do this simply? And is there a simpler version to this? We'll try to recall, what would you do if you had to simplify 1 over 1 minus x plus 1 over 1 plus x? So I want to simplify this. Now remember, when we add fractions, we need to have the same denominator. So here I want to figure out what's my LCD. And looking at the denominators, my LCD, the least common denominator is 1 minus x times 1 plus x. So this is something we've seen in our algebra classes. We're applying the same principle. A lot about mathematics is applying principles to new concepts. But really, it's the same. Inherently, it's not much different. We're just applying this same reasoning that we have here to an expression that has trig in it. So here I'm like, wait, 1 minus sine alpha and 1 plus sine alpha. I know for a fact to add two fractions, I must have the same denominator. So I must say, hey, LCD must be 1 minus sine alpha times 1 plus sine alpha. By the same reasoning, we have 1 minus x times 1 plus x in this simpler example. So the idea here is that I want to combine the two fractions together by first having both denominators being the same. Now, how do I make them the same? Well, what's the idea? After you find the LCD, what do? To each fraction, you multiply by its corresponding factor to make it LCD. So, for example, in this case, 1 minus x. If I want to make the 1 minus x denominator into 1 minus x times 1 plus x, I need to multiply the top and bottom by 1 plus x. And the same goes for the 1 plus x. How do I make that into the same denominator as 1 minus x times 1 plus x? I multiply the top and bottom by 1 minus x. Now, I can multiply these fractions across, and the result will be two fractions with the same denominator. I'm going to do the exact same thing here. 1 over 1 minus sine alpha. What must I multiply to 1 minus sine alpha to get 1 minus sine alpha times 1 plus sine alpha? I need to multiply by 1 plus sine alpha over 1 plus sine alpha. Then I have to add by 1 over 1 plus sine alpha. And I must multiply the top and bottom by 1 minus sine alpha. 1 minus sine alpha. Now, when I multiply the denominators, I get 1 plus sine alpha times 1 minus sine alpha, and 1 plus sine alpha times 1 is simply 1 plus sine alpha. Plus, multiply these across and I get 1 minus sine alpha over 1 plus sine alpha times 1 minus sine alpha. Again, we need our algebra, our algebra game to be on point. This is just algebra at this point. Two denominators, and they're both the same, and I'm adding them, so I can keep all the denominators the same. I can keep the denominator, do is add the numerators. So 1 plus sine alpha plus 1 minus sine alpha. And what happens? The sine alpha minus sine alpha goes away. The 1 plus 1 becomes a 2 on the top. Now, the interesting thing that occurs is in the denominator. Look what we have. 1 plus sine alpha times 1 minus sine alpha. And if I multiply these two factors here, I need to FOIL, right? So I need to multiply 1 times 1 and I get 1. 1 times sine, negative sine, I get negative sine alpha. Sine alpha times 1 is plus sine alpha. Plus sine alpha times negative sine alpha is negative sine squared alpha. So I'm going to continue number 5 over here. So 5, continued. So if I'm going to write this as 2 over 1 minus sine alpha plus sine alpha plus sine squared alpha. Minus, sorry. What cancels out here? It's the middle terms that cancel out, and we should have noticed that already because this looks like a factorization of a difference of perfect squares. So if I factor this difference of perfect squares into these two binomials, right? These two expressions with two terms, and I were to expand everything out, these middle terms would cancel out, and I'm left with 2 over 1 minus sine squared alpha. But then I realized, hey, what's 1 minus sine squared alpha? It's exactly cosine squared alpha. Remember this. I should be able to recognize 1 minus sine squared alpha is cosine squared alpha over 2. 2 is over it. And I can leave it like this because there's not much you can do after this. Or I can write it more compactly without the fraction, knowing that cosine is 1 over cosine, pardon me, is the same thing as secant. So I can rewrite this as 2 times secant squared alpha. And this would be what 1 minus sine alpha plus 1 over 1 plus sine alpha. What it simplifies to? It simplifies to 2 secant squared alpha. So that's the way we simplify trig identities. Right. Now let's look at trig applications. So this is section number 5. And let's see what can we do. So let's look at number 3. What does it say? It says that at point A underground, the angle of elevation to the top of a building is 24.1 degrees. And from a point B, which is 600 feet closer to the building, the angle of elevation is measured as 30.2 degrees. So we have 2 points on the ground, A, we have another point B. And we're making the angle of elevation to the top of a building, right? We have a building. We're assuming this is a 90-degree angle. And we have this angle here, which is 30.2 degrees. And this angle here is 24.1 degrees. And the distance between A and B is 600 feet. Now the question becomes is what is the height? What is this height? What is the height of the building? H. This is a tricky one because we have to try to figure out what this side is only by knowing the angles made between these 2 points at the top of the building and the distance between. So this one requires a little bit more of a understanding of how to apply algebra to solve these type of problems. So what is it that we know? We know these angles. We know the distance between A and B. And what don't we know? We don't know what this height is. Now what we can try to do is say, wait a minute. I know this is a right triangle. That's my saving grace here. It's a right triangle. So I know trig functions and how trig functions are related to right triangles. I know sine, cosine, and tangent can be applied here somehow, some way. Now, what is that way? Well, the idea is this. The idea is that I'm going to utilize this distance that I don't know. I'm going to call it something, a variable. I'm going to call it x. So x will be the distance between B and the base of the building. Now you're saying, wait, you just made the problem more complicated because now you have two variables that you don't know. And I would say, well, I didn't actually complicate it. I actually simplified it. The reason why is because now I can do the following. I can figure out the relationship between x and h for this triangle, and then I can figure out the relationship between x and h in this larger triangle. Because I have two unknowns, I need to have two equations in order to solve for those two unknowns. So that's the idea behind this problem here. So in my first triangle, so I'm going to call this 1, I'm going to call this 2. So triangle 1, in triangle 1, I should just write it up. Triangle 1. What do I know? I know that the angle is 30.2. The opposite side is the height, and the adjacent side is this x. So tangent of 30.2 degrees equals h over x. So I know that's true, 100%. Now look at triangle 2. And in triangle 2, we're looking at the big triangle, the big one. So the big one, look what we have. We have the angle 24.1 degrees. We have the height h, and we have this adjacent side. And this whole side here is 600 plus x. So in triangle 2, my angle is different, but my tangent function is the same. 24.1 degrees equals h all over 600 plus x. Now this is nice. Why is this good? Because I have two equations and I have these two unknowns that I can solve for. Now the question becomes, how do we solve two equations with two unknowns? Well, one way is utilizing a substitution method. And the substitution method is when we solve for one variable in terms of the other. So in this case, what can I do? I can do many things. I can say, what does h equal? Well, from here, I can solve for h. So let me solve for h. And how do I solve for h here? I want to get h by itself. So I must multiply x on both sides of the equation. So when I multiply x on both sides of the equation, I get that h is equal to x times tangent of 30.2 degrees. Now I can say, look, h has this expression in terms of x. Solve for h, I'm going to write in terms of x. Now I can replace h or substitute. I can substitute for h. And this becomes x times tangent of 30.2 degrees over 600 plus x, multiplied by tan of 24.1 degrees. And now look what I have. I have an equation with a single variable, just one. And I can solve this using algebra again. And don't get bogged down by what tangent of 30.2 degrees is or tangent of 24.1 degrees is. I know for a fact that this is some value. And for now, I'm just going to keep it in its exact form. I'm going to use my calculator at the end to figure out exactly what x is as an approximation, decimal approximation. But for now, I just want to get x by itself. That's all. Now, how do I get x by itself here? I need to multiply 600 plus x on both sides. And when I do that, I get x times tangent of 30.2 degrees. And this becomes, I can distribute everything here, and I get 600 tangent of 24.1 degrees plus x times tangent of 24.1 degrees. Now look what I have. I have everything now on a single playing field, right? All my expressions are in the numerator per se. I don't have the x no longer in the denominator. And now I can get all the x's on the same side. I need to subtract by x tan of 24.1 degrees minus x times tan of 24.1 degrees. And I get that 600 tangent of 24.1 degrees equals x times tangent of 30.2 degrees minus x times tangent of 24.1 degrees. And now I can factor the x, and I'm left with tangent of 30.2 degrees minus tangent of 24.1 degrees. And now I can get x by itself. I can divide this whole thing by tangent of 30.2 degrees minus tangent of 24.1 degrees. Are divided on both sides. And when I do so, these cancel. What am I left with? I'm left with x equals 600 tangent of 24.1 degrees all over tangent of 30.2 degrees minus tangent of 24.1 degrees. And this is when I need to utilize my calculator. And when I do so, I get 600 tangent, 24.1 degrees, divided by tangent of 30.2 degrees, minus tangent of 24.1 degrees. And I get that x equals 1992.638095. And make sure when you do this, your calculator is in degree mode. But this is not what I'm looking for, correct? I'm looking for what h is. That's the goal. My goal here is h. So I only found x to find h. And the nice thing is that x and h have this correspondence. So the height is equal to x times tangent of 30.2 degrees, which is the same thing as saying 1992.638095. I multiply this by tangent of 30.2 degrees. And when I multiply by tangent of 30.2 degrees, I get 1159.743065. And this is my height. And if you want to round to the nearest two decimal places, it'll just be 1159.74 feet. So this one requires a little bit more, but the ideas are pretty straightforward. I take this triangle, which I can take advantage of because I know the angle and the opposite and adjacent side, so I use tangent. I look at the bigger triangle and I realize, hey, I can also relate the angle with the opposite side, which is the one I'm interested in. And now this adjacent side is the same, it's just that I'm adding 600 to the x. And when I write these two equations, I realize I can solve for one variable with one equation and plug it into the other. And after this is really just, after this step here, it's really just the algebra part to solving an equation, except that now we have trig in our equation. And we solve for one variable, and we're able to plug it in to find the variable that we're interested in, which is the height. That would be the final answer. Okay. So that's trig applications. There's two more of these. Well, I think the other ones are a little simpler. So we can move on to graphs. So section number 4 are graphs. And the graphs of sinusoidal functions. So let's look at equations from graphs. So I want to find equations from graphs. And let's look at I. Let's look at what I looks like. So the idea is that this here is pi, this here is 2 pi. This here is 4, and this bottom value is -4. And in theory, this goes on to the right forever, to the left forever. And now the question is, what is the equation that represents this graph? Now, what must we know about trig or graphs of sinusoidal functions? We need to know the amplitude we need to know the frequency, the period, midline, and the phase shift, if any. So what is the amplitude? The amplitude is the height, quote unquote, of the wave, which is just the distance between the center and the max point, or the center and the min point. Well, this seems to be pretty apparent that the midpoint, or the midline, I should say, of this sinusoidal function is y equals 0. So I can immediately say that the midline is y equals 0. And if my midline is directly in between the max and the midpoints, that distance between the midline and the maximum is a 4. So the amplitude here is 4. My frequency is how long it takes to see one full curve. And this curve here starts at the center and goes up, then down, then up. This has the form of sine, the sine function. And so then how many sine curves do you see in this graph? This is one sine curve, and I see it in pi radians. So my frequency is pi. Now what is my period? My period is how long it takes to see. So pardon me, my period is how long it takes to see one full sine curve. And it takes pi radians. So yes, pardon me, pi should represent the period. The period is how long it takes to see one full sine curve. The frequency is how many sine curves do you see in exactly 2 pi radians. And I see here that I see 2 of them. And remember the relationship between frequency and period. What's the relationship? The relationship is that the period is equal to 2 pi over the frequency. And vice versa. The frequency is 2 pi over the period. And the phase shift, there is no phase shift because I'm starting exactly at 0. At x equals 0, y equals 0. So my sine function starts exactly here. So there is no phase shift. There is none. So with all of this, I can write the equation. Remember, my amplitude here is the vertical factor that I'm stretching it by. 4. I'm multiplying that by the function sine. What's my frequency? That's that value in front of x. Phase shift, there is none. And I add a 0 because that's the midline, but that's it. So this would be the equation. 4 times sine 2x. If I plot this graph in my calculator, I have to make sure that my calculator is in radian mode. This would be the graph of this equation. So that is an example of finding the equation given a graph. Now let's look at the next one, because the next one seems a little bit strange. But don't worry, we can do this one. So this one here, we have a graph that looks like a cosine graph, right? But if you notice, it's a little off center. It's not centered correctly. So that this one you should immediately recognize. You should recognize that this has a phase shift of some sort. It's 2 pi over 3. This is negative pi. Now this is the cosine curve, because we have something that goes up and down. Now there seems to be some kind of shift to the right because normally the cosine curve begins at a maximum, but my maximum is right here. So the question is, what is this distance here? What is this shift here that I have? So I don't know what that is, but we can figure that out. The first thing I want to figure out, though, are the easy things. The max is 1/2, and the min is -1/2. So my midline is right in between it. So my midline again here is y equals 0. This is my midline. And since this is my midline, my maximum point is that distance here. So this is my amplitude. My amplitude is 1/2. So this is 1/2. Now this is the crux of the problem. My question now is the frequency and the period. Now remember, what's the period? The period is how long it would take to see one full curve. In this case, it's one full cosine curve. Now, how do you find the period? Well, I want to find, from here, I see that I only have one full cosine curve. And I want to find what is this distance here. This is like a snapshot of the whole cosine curve that keeps on going. So what is this between here and here? How much is this? Because this difference represents my period. Remember, my period is how long you see one full cosine curve, or how long does it take for this graph to repeat itself. That's basically another way to see that. Now, how do you find this distance? I need to take the difference between it, right? 2 pi over 3 minus -pi/3. I want to find what is this distance here. Or you can think about this as from here to here is 2 pi over 3, from here to here is pi over 3, and then you add it up. And when I add it up, I get 3 pi over 3 equals pi. So my period is actually pi. My period is pi. So if my period is pi, remember, my period is also 2 pi over my frequency, which is my b value. So from here, how do I figure out my frequency? Well, I got pi equals 2 pi over my frequency. So then by a little bit of algebra, my frequency is 2 pi over pi, which equals 2. So my frequency here is 2. So far, so good. Now, the hardest part of this is to figure out that shift. Now, because my period is pi, what do I know? I know that this whole thing is pi. And I can divide my period into fourths, into quarters. So what's a quarter of pi? A quarter of my period. It's pi over 4. So that means that if I go from here to here, this must be an additional pi over 4. If I go from here to here, it must be an additional pi over 4. If I go from here to here, pi over 4, and finally pi over 4, because when I add all these up, I should get pi. So now the question becomes, what's -pi over 3 plus pi over 4? These are like the small little details that we need to figure out. So I need to have the same denominator, so this becomes -4 pi over 12 plus 3 pi over 12, which equals -pi over 12. So this point right here is -pi over 12. Now from here, I want to add another pi over 4 to figure out what this is. So I need to go from -pi over 12 plus pi over 4, which is -pi over 12 plus 3 pi over 12, which is 2 pi over 12, which reduces to pi over 6. So this point here is actually pi over 6. And this is exactly my missing value. So what did I do to my cosine curve, which originally starts from the maximum? I shifted it over to the right for pi over 6 units. So this is a horizontal shift to the right. And this is known as my phase shift. This is how much I shift the cosine curve to the right. So if I put this all together, what's the equation? The equation is y equals, remember my positive cosine curve starts at a maximum. My amplitude is 1/2 cosine. My frequency, what's my frequency? My frequency is 2. And make sure you remember x is being shifted to the right by pi over 6. So I have to subtract pi over 6 because this represents a horizontal shift. And since there is no vertical shift, this would be the final answer. So this is the equation that represents this curve from negative pi over 3 to 2 pi. So the tricky part, again, the tricky part here is only when there's this horizontal or this phase shift. That's the tricky part. But that's usually found very simply by first finding the period, dividing it into fourths. Because that's the nice thing about the trig and the sine and cosine curves, they're symmetric into fourths. You can divide them into 4 equal spaces. You can divide the period into 4 equal spaces. So there is the answer. Okay. So I'll do a few more and we can call it a day. So let's look at number 3, triangles. Section 3 on triangle. And there's one on law of cosines. So again, this is not drawing a scale, but it's just a figure here. And I want to find the unknown angles. Let's just find one angle. So let's find one angle. I'm going to call this theta. I want to find theta. And to find these other angles here, it's the same process. The hardest part, remember, to apply the law of cosines is to determine what is the angle and what's the corresponding side and seeing how they relate when you apply the law of cosines. So the law of cosines, remember, how do we set it up? We set it up, and there's like 3 different formulations for it using the variables. But all we really care about is how are those values in the formula related to one another. And so we have a side squared, right? That side that's going to be squared by itself on one side of the equation is the side that's opposite the angle in question. So this will be 100 squared plus, then the other 2 sides will be the other sides that are being squared, and minus 2 times the other sides times cosine of the angle that I want. So this is the hardest part of this problem. After this, it's algebra and using the calculator. So let's use our calculator. We know 100 squared is 10,000. 120 squared is 14400. Oh, 14,400. And then 65 squared is 4,225. And then 2 times 120 times 65 is 15,600 cosine theta. So at this stage, it's just finding the result, the angle that we're interested in. And here again, it's just algebra. And the good thing is I have a calculator that I can utilize for the computation, and I get 18,625 minus 15,600 cosine of theta. This is 10,000. Subtract by 18,625, 18,625, and I get that 10,000 minus 18,625 is negative 8,625 equals negative 15,600 cosine theta. And again, I want to get theta by itself, so I need to divide both sides by negative 15,600. Negative 15,600. And this becomes positive cosine theta. And this becomes negative divided by negative 8,625. 15,600. Now, I want to figure out what the angle is, theta. The only way to do that is utilizing inverse cosine. So if cosine of theta equals 8,625 over 15,600, then theta can be rewritten as cosine inverse of 8,625 over 15,600. And this is when I use my calculator, cosine, inverse cosine of 8,625 divided by 15,600. And I get that my angle is 56.434, and this goes on forever, degrees. So if I round it, to decimal places, this is my angle. So law of cosines and even law of sines are just applying the formula, and after that, it's knowing what to do in terms of algebra. So that's why algebra is important. That's why we learn algebra in the first place, because with algebra, we have the tools to apply it to higher level, more advanced concepts. But algebra is a fundamental part of mathematics that we need to master. So let's do a few more things. So in section 2 now, we have several things here about inverse trig. So let's look at values of inverse trig, part 3. And let's get number 3. So number 3 says that secant of the tangent of the inverse tangent of 2/5. What is this equal to? And I wanted an exact value. I want the exact value. And whenever you hear the word exact, to think of radical. I want the radical expression. So radical expression. I do not want the decimal, not decimal. Now, how do we take care of this? We always go from the inside out. So the inside of this expression, what do we have? We have an angle. Tan inverse represents an angle. I'm going to call it theta. So tan inverse of 2/5 equals theta, which means that tangent of theta equals 2/5. Now, I can create a right triangle with these current sides, the opposite side and the adjacent side. That's what tangent of theta represents, an opposite side of 2 and an adjacent side of 5. Now, how do I find the hypotenuse? I apply the Pythagorean theorem, which is 2 squared plus 5 squared, which is the square root of 29. So now I know that my angle here is this represented in this triangle whose sides are 2 and 5 and whose hypotenuse is radical 29. And I want to find secant of this angle. Secant is 1 over cosine, which represents hypotenuse over the adjacent side of theta. The hypotenuse is radical 29, and the adjacent side is 5. So this would be the exact value of secant of tan inverse of 2/5. It's exactly radical 29 over 5. Okay. Then we have, let's see. Make sure you know how to find the value of trig functions. This is fundamental. I think it's called part 1. Yeah, part 1. So if I want to figure out, for example, tangent of negative 150 degrees, and of course I want this in exact value. So this is the whole point of this. I know I can plug this in my calculator and get an answer, right? But I want to use my knowledge of trig, and I don't want to lean on my calculator to find this value. So the first thing is I need to figure out where is negative 150 degrees in the quadrants that I have. So remember, when I have a negative angle, I'm going in the clockwise direction. So this would be 0, this would be negative 90 degrees, this would be negative 180 degrees, this is negative 270 degrees. And so negative 150 seems to lie somewhere over here. This represents negative 150 degrees, right? So I should write it right here, negative 150 degrees. Now, what did I realize? Negative 150 degrees is in quadrant 3. Step 1. Step 2. So this is step 1. Step 2 is tangent is positive in quadrant 3. So then I don't have to worry about that negative sign anymore, right? So it's tangent. Tangent is positive there. And then what I need to figure out is my reference angle. What's my reference angle? My reference angle is that positive acute angle that's made between the terminal side and the x-axis. And this happens to be 30 degrees. So tangent of negative 150 degrees is equivalent to tangent positive of 30. And what's the tangent of 30 degrees? You should know this. Radical 3 over 3. This is something that we should know based upon our study of the special right triangles and the trig ratios. So, and this is the same idea for any one of those expressions. We want to figure out where is the angle. Is the function positive or negative in that quadrant? What is the reference angle? Because the reference angle gives us, we should know the reference angles, 30 degrees, 45 degrees, 60 degrees, 0 degrees, 90 degrees. These are the reference angles. They're like the basic ones that we should know the values for sine, cosine, and tangent of. And once we have that, then we can figure out the value, the exact value. Okay? So that's how do you find the value of trig functions part 1. If you want, we could do something. We can do 5. So part 5, which has a radian measure of an angle. So some of you may still not be so comfortable with radians, but we have to become very comfortable with radians. So this is cotangent of negative 22 pi over 3. So this may look a little scary, right? Negative 22 pi over 3. So again, the same question becomes, where is this angle negative 22 pi over 3? And because it's negative, we know we're going in the clockwise direction. So again, this would be negative pi over 2. This is negative pi. This is negative 3 pi over 2 because we're moving in the clockwise direction. So I have negative 22 pi over 3. Now this is when it gets a little crazy. Now what is 22 pi over 3? Now whenever we deal with this kind of situation, I always like to not consider this a little too much, this number in front of pi, and just look at pi over 3. So I'm going to be looking at slices of pi divided into thirds. So this pi here is divided into thirds. This will be negative pi over 3. This will be negative 2 pi over 3. This will be negative 3 pi over 3. But negative 3 pi over 3 is negative pi. And then slowly, I start to see this is negative 4 pi over 3. This is negative 5 pi over 3. This is negative 4 pi over 3. This is negative 5 pi over 3. And this would be negative 6 pi over 3, which equals negative 2 pi. Do you see that? So this is negative pi over 3, negative 2 pi over 3. Negative 3 pi over 3, which is negative pi, negative 4 pi over 3, negative 5 pi over 3. So this is where I'm going. I'm going from here to here to here to here to here to here. And I'm just going to be going like this. Oh, no, not here. I'll be going from here to here to here to here to here to here. That's what I'm doing. So I'm doing this 22 times. This is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. These are what are called coterminal. These are coterminal angles. I found the angle. I found it. So now I know that this angle, with a little bit of work, is in the second quadrant. So quadrant 2. So theta is in quadrant 2. Step 1. Step 2. Cotangent. Cotangent is the reciprocal of tan. So essentially, the sign of cotangent depends upon what the sign is of tangent. So tangent or cotangent is negative in quadrant 2. I know that because all students take calculus. Only sine is positive here, cosine and tangent negative here. So this must be that there's a negative in front of the value will be a negative. Then what do? I take cotangent of, now what's my third thing I need to know? The reference angle. What's my reference angle? Of this angle. Remember, we're dealing with pi over thirds. This is a pi over third here. So my reference angle is pi over 3. This is pi over 3. Pi over 3 is also known as cosine of, it's also known as the angle of 60 degrees. Cotangent is 1 over tangent. So let me just put that over here. 1 over tangent of pi over 3. But tan of pi over 3 is tan of 60. And tan of 60 degrees is 1 over radical 3. So this whole expression equals negative 1/3 radical 3. And if you want to rationalize it, this becomes negative radical 3 over 3. So these are the steps that you need to apply in order to find the value of a trig function. First, find where the angle is in the quadrants. Determine the sign of the trig function in that quadrant that you're in. Find the reference angle of this angle by figuring out where you are, and then find that difference between the terminal side and the positive x-axis. And then that's going to be one of your reference angles that you must know the value of for the trig function. And you apply it, and you get the final answer. So we got to make sure we know how to do that. And for those of you who have joined us, if you have any questions, please ask them now. Any at all. If not, I'll just finish up with terminal points, because I feel like we should drive that home. So this is section 1. Terminal points. So let's find the terminal point. So terminal point for number 3. Theta equals negative 7 pi over 6. So the terminal point is the point on the circle, x comma y, on the unit circle. I want to know where negative 7 pi over 6 is. So remember, this is negative pi, this is negative pi over 2. And remember, whenever we deal with things like this, we always want to figure out how am I dividing up pi? This second half of the circle, how am I dividing it up? I'm dividing it into 6 equal slices. This is 1 slice. So this is 1 slice, 2 slice, 3 slice, and then 4 slice, then 5 slice, 6 slice, and then 7, 8, 9, 10, 11. So I'm just dividing it up into 6 6 slices on the first half and then second half. So this is going to be negative pi over 6. This is negative 2 pi over 6, which equals negative pi over 3. This is negative 3 pi over 6, which is equal to negative pi over 2. This is negative 4 pi over 6, which equals negative 2 pi over 3. This is negative 5 pi over 6. This is negative 6 pi over 6, but that equals negative pi. This is negative 7 pi over 6. So this is going to be in this is in quadrant 2. And the idea is that my terminal point on the unit circle, x comma y, is given by cosine of my angle, comma, sine of my angle. That's the whole point. That's the whole connection. Cosine of my angle is negative 7 pi over 6. Cosine is negative 7 pi over 6, comma, sine of negative 7 pi over 6. It's the same angle that we're dealing with. And now the question becomes this: what is cosine of negative 7 pi over 6 and what is sine of negative 7 pi over 6? And we're doing this individually. And remember, this is exactly what we did just a minute ago. How do I figure out what this is? First, figure out what quadrant I'm in. Found it, quadrant 2. Cosine is what? Negative or positive in quadrant 2? It's negative, so this will be negative. Cosine of, what is my reference angle to negative 7 pi over 6? Well, it happens to be pi over 6. So this is cosine of pi over 6. But cosine of pi over 6, for those of you who are more comfortable with degrees, is 30 degrees. So what's cosine of 30 degrees? You should know it's negative radical 3 over 2. So my terminal point for my x value would be negative radical 3 over 2. Now I'm going to do the same exact thing for sine. Sine of negative 7 pi over 6. The angle here is in the second quadrant. Sine is positive in the second quadrant. Negative 7 pi over 6 has a reference angle of pi over 6. And pi over 6 is 30 degrees. So sine of 30 degrees is positive 1/2. And this makes sense because I'm in my second quadrant and my x coordinate is negative. My y coordinate has to be positive in the second quadrant. So that is the terminal point. That is the terminal point related to my angle negative 7 pi over 6. Okay. So again, last call. For those of you who are online, is there anything you want to cover? Any questions you have? You can type it in the chat box. If not, then yes, that is the first thing we did. But if you would like to see it again, we can do another one. We didn't do all of them. So for the trig identities, we didn't do all of the trig identities questions. We just did, I think, only 2 of them, of the 5. So if you want to see one of the other 3, we can do that. All right, so let's see. We did trig identities. We did number 2. Yeah, we did number 2 and number 3. And number 4, number 5, we've done them in class, but I can do them again. And number 1, I think we've done them as well. So yeah, let's look at number 4. So number 4. So this is section number 6 on proving trig identities. So number 4. Number 4 is 1 plus secant squared x over 1 plus tangent squared x equals 1 plus cosine squared x. So this is a trig identity, and they're telling us these two things are equal. What we want to do is say, how is that possible? How can we show that it indeed is true, that the left-hand side is indeed the same as the right-hand side? That's all. That's all it is. And all we want to do is be able to apply those trig identities that we originally know and a little bit of algebra to go from the left-hand side to the right-hand side. So let's look at that. So the left-hand side is 1 plus secant squared x over 1 plus tangent squared x. So we look at this, and usually we start with the left-hand side because there tends to be a tendency that the left-hand side is a little more complicated to deal with than the right-hand side. Because the right-hand side is a little simpler in this case, most of these examples. So we're going to see how can we make this simpler? How can we simplify the left-hand side? If we can, if it's possible to get to the right-hand side. Now we study this and we see, wait a minute. What's 1 plus secant squared x? Do we have any trig identity that relates 1 plus secant squared x with some other trig function? We have secant squared x, but it's not quite 1 plus secant squared x. So that's where we have to go back to the identities that we must know. Sine x squared plus cosine x squared equals 1. I must know this. This is the Pythagorean identity. From here, I have little, like, you can think of this as like a father or a mother, and these are like the offspring. This produces sine squared x equals 1 minus cosine squared x. And the other one that comes out of this is cosine squared x equals 1 minus sine squared x. And then the other one, when you divide everything by cosine squared x, you get, I guess I could call it C. This would be 1 plus tangent squared x equals secant squared x. And then the last one here is 1 plus cotangent squared x equals cosecant squared x. So these are the ones that stem from the same identity. So if you know this identity, you should be able to come up with the rest. So then you realize, okay, do I have 1 plus secant squared x here? I have a secant squared. I have a 1, but it's not being added to the secant squared. But what I do have is 1 plus tangent squared. I have that 1 plus tangent squared is exactly secant squared. So I'm going to replace that. So then now I'm at this juncture here. And then I ask myself, what can I do from here? From here, it's just algebra. There's no more trig. It's just algebra. And this is something I have to reiterate and stress, that algebra is something you have to develop, and it has to be excellent. At this point, especially when you go to calculus, your algebra has to be excellent. It can't be so-so, because you don't want to lose out on making, having understanding of higher level concepts, but you're still dealing with how to solve an equation or how to simplify things. You can't have that problem anymore. So that's why we try to take care of that now. So from here, I'm like, what can I do? What I can do is I can split the fraction. Again, this is just algebra. I split the fraction because this is a sum in the numerator, and you have the same denominator, secant squared x. And now what's nice about this is that secant squared x over secant squared x is 1. Anything, doesn't matter what it is, divided by itself, unless it's 0. 0 divided by 0 is not 1. But anything else divided by itself is always equal to 1. And now look what's 1 over secant squared x. It's the same thing as saying 1 over cosine squared x. But 1 over secant is 1 over cosine, which is the reciprocal of cosine, right? Secant is the reciprocal of cosine. Cosine is the reciprocal of secant. So 1 over secant is cosine squared x plus 1. But 1 plus cosine squared x plus 1 is exactly the same thing as 1 plus cosine squared x. So this is indeed 1 plus cosine squared x, which is indeed the right-hand side. So I utilized the trig identities with a little bit of algebra to demonstrate that the left-hand side indeed is equivalent to the right-hand side. And that's it. I know the proving stuff, right? This idea of proving is something kind of new to some of you, to many of you maybe. But this is what we're looking at now. We're not looking for what's the answer anymore. Is it a numerical answer? Or we're not looking at the final product. We're looking at how do we develop. The answer now is a explanation. This is my explanation of why the left-hand side equals the right-hand side. And that's what we want you guys to be able to do. Show that the left-hand side, through some algebra and some trig identity recognition, that the left hand indeed equals the right hand. And this idea is being applied every time you do proving trig identity. It's the same framework. Just sometimes the expressions might be a little different. Sometimes you may have to deal with some other algebraic principles and apply those, but the idea is the same. So hopefully that makes a little bit more sense. And again, this is very important. This here is without this, you can't do anything. So anything else? So we covered trig identities, simplifying them, proving them. We've covered one problem on trig applications. We did those two problems that we need to find the equation from a trig graph, from a graph of a trig function. So that's in part 4. We did law of cosines for question number 1 and found one angle. And we did values of inverse trig, values of regular trig functions, and terminal points. So that's what I've covered in this past hour and a half. So anything else? This is your final chance at being answered live through YouTube, which is an awesome tool, by the way. And the good thing is that all of this will be uploaded immediately after we conclude. Alrighty. So, well, I hope this serves I hope this is useful to those who do watch it, and I'll put the timestamps for all the different topics that we covered, so it's a little easier just to sift through the video, so you don't have to go through the whole thing if you don't need it. Okay. All right. So any more questions? There's no more. It's okay. I hope this helps any and all of you who check this out. And best of luck tomorrow on your exam. I'll be there earlier, so if you guys need, any last minute questions face to face, I'll be there tomorrow as early as possible. I'll be there probably before 8 a.m. so you can catch me then. Alrighty, so best of luck, and I'll see you all. Yep, I'll see you all tomorrow. Okay. All right. Signing off. Take care, guys.